looking at this some important days. Let's start with the lecture, essentially topic 1. And I do like to say the space of 3 hours. Maybe we'll finish the topic a little over 2 hours, okay? So you can go home early. Any question? We have lecture only up to late October, okay? And we're teaching essential material. You can do your design project for the 4th semester, okay? You're supposed to turn your final project report Friday before Thanksgiving break. While you enjoy your turkey at home, I'll be reading your report. Don't you know that? So let's get started. Now, what's new this semester? We are focusing on design. In previous year, you deal with analysis. You know a reactor, you know feed, you calculate the output product. This semester and next semester, you're trying to create a process design. And you'll be doing industrial project next semester. In some of the project, they said, I have a byproduct, I don't know how to utilize it. Can you do research, find out potential reaction, potential product, which reaction path is best? And you design a process. Tell me investment costs, operating costs. So, there are also situations you know the output. I want to make certain product. You do not know what will be a good feed. So, in both situations, you need to do research, create synthesis. Now you look at this initial flow sheet, initial synthesis. Once you have an initial process concept, and you can use Aspen Plus to do analysis, mass energy balances, sizing and costing equipment, economic evaluation. And this process is iterative. If your conversion now initially set at 80%, or about 95%, will you change your process flow sheet? That going through a sensitivity analysis, parameter optimization. So this whole thing finally comes with a final flow sheet. So the topic, first one, how do you create a flow sheet of a process? And today we will focus on separation part. Let me start on page 2. This is National Design Competition. I want you to focus on NAFTA. What is that? What is NAFTA? Page 3. Now, you'll be doing a lot of your own research. If you've got a cell phone, Google it. Now to give you AI composed answer. I will tell you the answer I gave you is wrong. You cannot trust everything. If you go to Google, first answer, they tell you NAFTA, okay, boiling point 30 to 200 degrees C. That is what Google AI gives to you. You can check it out yourself. That's not right. But on the same Google answer page, you go down 4 to 5, you find an answer U.S. Energy Information Administration. That's more legit answer, official answer. You find out the answer is 50 to 200 degrees C. Or 122 to 400 degree F in this range. So the difference between 30 and 50. Yeah? What? Let me see. Let me enlarge it, see what happens.
I think he's just saying you put it in the wrong box.
Oh, what? It's okay. 50 is correct answer. Okay. All right, now. Oh, I put the wrong box. Oh, yeah, carbon atom. I'm sorry. Carbon is about 6 to 12, sorry. 6 to 12. Thank you. Carbon 6 to 12. Okay? Thank you. Now, the reason I want to mention about naphtha is this. We want to develop a separation to produce hydrocarbon from naphtha. The most popular process to produce gasoline from naphtha is called cracking, pyrolysis, adding heat. And this is a block diagram. Naphtha steam thermally decompose this into hydrocarbon, quench, fast cooling, and this generates a lot of steam, a lot of heat, generate a lot of heat. You can use that heat to convert boiling water to steam. Now, you look at hydrocarbon you produce. Hydrogen, carbon 1, carbon 2 minus, carbon 2 minus, carbon 3, carbon 4. What is special about them? Boiling point negative. Low temperature, right? Refrigeration. Today you're going to learn, if you have low temperature component, you want to separate them, you need high pressure. Raise the pressure, use a compressor. Before you go through the separation, okay? You want to do it low temperature distillation using refrigerant, you better apply high pressure. That's one of the rules in engineering design you learned today. Our goal today is this. This is the black box. How do you develop a sequence of separator to get pure component product, or pure component product? Okay? So, look at next page. Two potential solutions, sequence A and B. Hydrogen, carbon 1, ethylene, carbon 2 minus, C2, propane, carbon 2 minus, carbon 3, carbon 4. You notice in this separation, you make a cut here first. Then the remaining component, make a cut here. And lastly, make a cut here. That is sequence A. The other option, make a cut here. And our goal is get hydrogen carbon a single product. So, go make a cut here. And finally, get that. So, you notice in both sequences, the separation, carbon 2 minus carbon 3, carbon 2 minus carbon 2, those are in the later step 3 or 4 of the sequence, right? So comparing the two, can you create those two sequences to carry out separation in a matter of minutes, less than 10 minutes, with simple hand calculation? That's the goal today. At the end of a 2-hour lecture, you should be able to do it, okay? This is the creative exercise. Now, what's the challenge? Heuristics, they have a textbook. We have 7 components. You want to separate into 7 pure component products. You have 132 options. If you use one separation method like ordinary distillation, you're adding heat to the bottom, removing heat from the top, using condenser, reboiler. Okay? Or if you have 10 components, close to 5,000 options. So this is our challenge for the 7 component separation. What if I make the life more complicated? You have to use 2 separation methods. One is attractive distillation. You are adding a solvent, phenol. Your primary component in the feed, toluene, MCH, methylcyclohexane. What's special about those 2 components? Boiling point, 100.6, 100.9. The boiling point difference, less than 10 degrees, is a challenging, difficult separation. So you put the separation, you add a solvent. Typically, solvent has higher boiling point than compared to primary component, 182 degree phenol. The way you do it, in the first column, your low boiling component, toluene, is solvent, will come to the bottom. MCH, go to the overhead. Now, solvent is an external component you add it to the system. How do you recover phenol on the bottom product? You have a solvent recovery column. And you notice 182, 100.9. There is a boiling point difference about 82 degrees. So this is an easy distillation operation, right? And low boiling species, T, toluene, high-boiling species phenol. So you get your two primary products in the overhead, you recover the solvent and recycle back. In actual practice, you might have some phenol, tiny amount, leaving overhead here, maybe tiny amount of phenol losing to the overhead. So normally you will have a solvent makeup, adding a small amount of phenol to make up the loss through the two products. This is the structure of attractive distillation. Now, let's look at another example with attractive distillation. Page 5. I hope I'm not teaching too fast. Can you follow? Now, here's the problem. A, B, C, D, E, F. Our goal is to get DE to isomer in a single product. A, B, C, D, E, F. What is a good flow sheet? Let's look at here, composition, mole percent. Metal 1, purely based on boiling point differences. Now, here's the term, relative volatility. First, K factor, Ki, more fractional component I in the vapor phase. Xi, more fractional component I in the liquid phase. Ki, Kj, another component Yj, Xj. This is K factor. What is relative volatility? Ratio of Ki over Kj. What's special about relative volatility? If this less than 1.05, that is a very difficult separation. What does that imply? Your column may need a lot of equipment stages, very tall. Okay? It costs you more. So, if there are situations, relative volatility is less than 1.05, normally we would not use ordinary distillation. Okay? Let's look at here a given problem. Between the two components A and B, relative volatility 2.05, B and C 1.18. Trouble right here. You want to split between C and D. Relative volatility too small. And E and F 2.5 is okay. D and E, you do not want to split it. It's a single product. So, what do? You add a solvent. In this case, the solvent is furfural. What's in the solvent? You find out relative volatility or boiling point between any two components. You look at this changes from 1.03 to 1.70. What's in the solvent? Relative volatility improved from 1.03 to 1.7. So that is more easy separation, requiring less number of ideal stages. So that's a possibility. So in this case, look at here. A, B, C, D, E, F. We're going to learn what's the reason you split F first. We're going to learn that. CD or DE is one product. DE one product, right? And CD is difficult. So, difficult. And we need to add solvent. Furfural, right? So, what are the remaining options between A and B, between B and C? Okay? We're going to learn how to make that decision today. In case you split AB first, so C, D, E. No, D is a single product. Here, there's only one split between C and D remaining, and that requires you to add solvent. Method 2. Increase the relative volatility to 1.7. CDE, solvent. That is the flow sheet. I'm going to learn how to do this after we learn the heuristic in a minute. Next page. The same reference. Henry, University of Houston, Cedar, University of Utah, both have retired now. He said, if you have T separation method, in our case, T equal 2, ordinary distillation, attractive distillation. How many components we wish to separate? In this case, 1, 2, 3, 4, 5, 6. But it doesn't matter. On the previous page, we learned with one method, 10 components, 5,000 options. With two methods, 10 components, 5,000, increase to 10 million. Our life is too short to deal with this, right? That's why you need to learn what is the best method to develop separation sequences. Now, I'm going to teach you the best method. The word best is not according to me, according to all the latest textbook, okay? Who wrote the article? I'm going to tell you why it's the best at the end, why other methods are bad, okay? So you learn a lot of stuff through our own previous research. The key word is heuristics. What is heuristic? There are some rule of thumb. For industrial practice, people use it in industry all the time. Some of them, people go through some derivation analysis to validate them. Other, based on engineering experiences. Okay? So, now, you don't need to read this until I finish teaching it. Let me see. Okay, from page 7 to 15, the article. Okay, let's go to page 15. Heuristics, rule of thumb, based on engineering experience. There are several types. Method, design, species, composition. Different type of rule of thumb. The key to our method is called rank order. You notice here, I listed 2 heuristics here. 1, 1, 2. This is heuristic number 1. Okay? This is heuristic number 7. Rank order means the one listed early is most important. Least important. Okay? If heuristic I'll give you in a minute. Okay. Go to page 16. 16. I have the number there, easier to explain. All we need to learn today, 7 heuristics that enable us to solve the 2 example problems in a matter of minutes. Here are the 2 heuristics, 3, 2. So, if heuristic tell you in method 1, to go this way, heuristic 7 tell you go that way, you listen to the heuristic at the top. Most important. This is least important. Okay? I'm going to go through each one of them one by one, and then we come back to summarize it. Okay? Page 17. Heuristic number 1, especially for vapor-liquid separation, favor ordinary distillation. Here, when you talk about heuristic, you often see the term, all things being equal. Every other condition almost the same. In reality, this doesn't happen very often, but close to be equal. Favor separation method that is only heat, energy separating agent, like cooling water, heating steam. That is for condenser with boiler. Okay? We call that energy separating agent. Avoid using mass separating agent. I don't like the term, mass separating agent. That's a dull English. Plain English, solvent. Okay? Avoid using solvent. Why is that? Solvent is not present in the process. When you add an external component into the system, you need to remove it. You also need to add a solvent recovery, right? Solvent. that require extra cost, right? So, first heuristic, say in plain English, very simple. If you don't need external solvent, don't do it. Just use ordinary distillation, adding heat, removing heat, right? Favor ordinary distillation. When do you use attractive distillation? Relative volatility less than 1.10 or even 1.05. That is a very challenging ordinary distillation. In the example, we have 1.07, right? You will add the solvent, MSA. In the example, we have relative volatility go from 1.07 to 1.70. Improve the separation, right? So, this heuristic, all common sense. Making sense? All things being equal, favor ordinary distillation. Now, if you have learned Finsky and Gilliland, did you learn that? In your separation course. Shortcut design of distillation column. Have you done any exercise? You forgot it, huh? How do you estimate component distribution? Suppose we want to split between AC4 and IC5. We call this light key component, heavy key component. Any component with boiling point lower than light key, we call that lighter than light key, LLK. Any component with boiling point higher than heavy key, HHK, heavier than HK. So how do you estimate component distribution given the feed, 100 pound per hour, feed composition, GI, FI, molar flow rate of feed. So, this is very simple. Normally you assume at least 0.98 on light key, 30.98, 30.02, 98% or more light key goes to distillate. Remaining 2% goes to the bottom. That assumption. How about heavy component? Just 20 plus 0.98, 20 times 0.02. Now, how about others? This lighter than light key or light component. This light key, you can assume all of that component goes to overhead 0, 0. How about heavy than component 15, 20, 0, 0. All the heavy component goes to the bottom. So you add together, that gives you distillate flow rate the sum volume flow rate, right? Sum. And you can find mole fraction of each component, 5 divided by total, 10 divided by total, right? That's how we estimate it. You may not need that for this first assignment, just explain it, okay? So, to summarize, first heuristic, favor ordinary distillation. Let's go to the next one. What is the second heuristic? On page 16, you see second heuristic, avoid vacuum and refrigeration. That's the second heuristic on page 16. Now, here's some extra about adding a solvent. Why is it a good thing to do or bad thing to do? How much more you need to improve relative volatility before you apply attractive distillation? This is Mr. Suter. And in this course, you learn a lot of who's who in chemical engineering. You just learn one, Frank Wilbur, right? Who is this gentleman? He's a recipient, AICHE, Professional Progress Award. Less than 45 years old, who make good technical contribution to the field. What contribution? Separation. This is one of his conclusions, the plot. You look at here, alpha for ordinary distillation. Alpha for ordinary distillation. Here, alpha for attractive distillation. Or liquid-liquid attraction. Let's learn what this says. If your relative volatility 1.66, that's here. You're at a vertical line. You divide this plot. Attractive distillation, liquid-liquid attraction. He said, if you find a solvent that can increase this relative volatility, here is 2, 3, at least 2.40. 2.5, 2.6, then that is worth it. Minimum should be 2.4. For liquid-liquid attraction, partition coefficient should be minimum 8. Okay? That is one of his conclusions from his paper, 1965. Okay, keep going. Now, second heuristic. I need to introduce to you all 7 heuristics before we apply the two problems, then explain the homework, then you go home. Let's go one more heuristic before I take a break. Avoid vacuum and refrigeration. Vacuum is low pressure. Refrigeration means low temperature. Both are costly. All things being equal, you prefer high pressure, high temperature. You do not want low pressure, low temperature. If vacuum operation is required, consider using solvent, liquid-liquid attraction. Refrigeration, low temperature required, you might use liquid-liquid absorption, but those two are less important. Let's look at the first one, page 20. What is the reason you want to avoid low pressure vacuum, low temperature refrigeration? This is a cause for heating. This is a cause for cooling. Cooling means go to low temperature. That could be refrigeration. Now, you want to use cooling water in a chemical plant, CW. Do you know what are the typical operating range temperature? How many degrees C to how many degrees C? If you have cooling water, you want to cool down a stream. What is the temperature rise of this cooling water? Uh-oh, no answer. 35 to 45. Now, you look at here, there's cooling water. What if you want to use much colder temperature? You need to use ammonia, liquid helium, liquid hydrogen, right? And to lower the temperature more. And those are expensive. Liquid nitrogen. Look at liquid nitrogen, okay? Liquid helium, that's troublesome. You want to deliver liquid helium to Virginia Tech, costly, right? Now, heating, look at, you can use steam. Steam has an advantage. You have low pressure steam, medium pressure steam, high pressure steam. You have different temperature level, right? In general, heating cost increases. You look at the slope, much smaller than cooling. So, this says, avoid refrigeration is because of that. Refrigeration is very low in temperature. Now, Mr. Shooter, he's a good engineer. He gives you this plot. Operating temperature minus 100 to 500, 600. Pressure 0.1 atm, 1, 10, 100. So here is high pressure, is low pressure. That's called vacuum operation. What does plot tell us? It said this curve gives you the recommended temperature-pressure combination for good chemical plant. You have 200 some degree. If you use low pressure, you prefer to use high temperature. If you have low temperature, that is refrigeration. And good operating condition, high pressure. Now, let's get back to the beginning. On page 3. All the boiling point for hydrogen, carbon 1 to carbon 4, negative. You want to separate them, all this light hydrocarbon. A good operating condition is high pressure. That's why there's a compression before the separation. And the good combination is low temperature distillation, typically done at high pressure. So, if we put that down, low, high, temperature, pressure, combination. Okay? Is this a good way? You see, no. High temperature, no, that's not a good way to write it. No. I think that's the way to write it. That's the way to write it. Pressure, temperature, right? You have low temperature, refrigeration. Low pressure, vacuum. Hell no. Agree? Low temperature, high pressure, yes. High temperature, that is yes. High, hell no. Making sense, right? Okay, let's take a break.
This is just like
Yeah.
oh, it's yeah. Taking 2 courses right now, interview labs. Yeah, and you'll, I'm in 3 labs.
You did. Sigma, I had it on my phone. You know what? What will happen? He will be a couple of times. When you two cars from each other, there's no 2 cars in that building. And this party after is all.
So you're full time? Okay. So you still in mining? Grad school or see what happens. See what Where would that be, Tennessee? Yeah. In Chemie?
Yeah, you can do that yet? Which? College? Graduating, can I get with that?
Quite the market.
So you are going
It's higher.
There's no way. Just to help with my job, there's no way.
Yeah. So it's not bad. It's not bad at all. I think this is my favorite day. No, less than right when he's doing something.
This is insane. Like, actually insane.
I wonder who wrote this song. Who wrote it? For this course? No. I haven't looked for this or process materials yet. I haven't done any for this one or process materials.
There's no way this needs to be 3 hours.
I'm just not going to. I'm just not going to until they make us do it. I'm so confused by the first one. I feel like he's explaining for you also. I just sometimes have like.
Why are they so
I could just do without the yellow.
The mic cutting in and out actually doesn't help. Gives me like a moment of relief and that's right up to it. Like,
That's why it's like that's what happens when you keep photocopying. Because it's like once you say no to the risk, I don't know.
did any resume conferences yet?
Have you?
Yeah. I was literally the first one, because he did it, I was feeling right before Wednesday class.
Yeah.
So I guess he just printed it out right after that. And then he did it literally right in front of me, and I was like,
You just watched you mark it up?
the funny part was I watched him start, and I was like, oh, this looks too bad. And then like, I looked down like 10 or 15 minutes later, covered. I was like,
Did he give it back to you already?
yeah, I got it back.
Were they like meaningful notes?
They were, but it took me like just 30 minutes just to like read it. Struggling so hard. He doesn't do that handwriting, but when he tries to write small, it just so it's a really good
I haven't gotten mine back yet, but we'll see. Hopefully.
I think I didn't really originally I had a lot of white space on it, but then after incorporating like some of his initial suggestions, like I didn't follow the slides, so I actually followed the slides and there's very little white space. I don't know.
Yeah, I had some white space at the bottom, and I didn't have a word section or something like that, so I added it in. But then to make it enough lines so that it didn't look weird, I had to make the text smaller, so I know it's just going to be like a big red circle. But I just wanted to fill in the space.
I thought about changing the text too, and I was like, well, I feel like this lawyer could probably just like 10 20.
I think mine is 12.
Yeah, 12 is good. I made mine 11 just to get a little extra space.
Yeah.
But I thought about going to 10 for expo. Then I knew when I was doing this, and I was like, maybe I should make it 12. I thought about it. I kept it at 11. I kept it in the middle ground. Yeah. Make everybody freedom.
Okay, let's continue. Listen, if you email me your memo, most likely you already got my feedback. As far as your resume, there are 84 copies I need to look at it. I think I finished about 35. I'm gonna have a long weekend. And normally when I finish reading, I scan and send it back to you. You fix it. There's no grade for both assignments. Just teach you how to write memo, learn about Frank Wheelbrand, help you find job. No grade, don't worry. Okay, let's continue. The next heuristic, common sense. Here, look at the example here. A, B, C, D. BC is a single product. The next example, BD is a single product. What do we mean by all things being equal? Here's one example. Mole flow rate is same. Boiling point difference is the same. This is what we mean by all things being equal. Now, think about it. A has the lowest boiling point, right? So, you split out initially A from BCD. And then BC is single product. Obviously, you want to split here. Wahoo engineer might do this. You think so? Wahoo engineer might do it. Okay? Hokie would not do it. Right? How about this one? You have no choice. Because your product is B and D. So you still need to go like that and mix together. So This heuristic favors smallest product set. That's not plain English. Plain English is don't split multi-component product. Does that make sense? So, you do not want to split BC, right? Okay, this heuristic is simple. You do not even need to read the text, right? Common sense. All right, next heuristic. Page 22. This one is easy. We started with ordinary distillation, choosing separation method. We want to avoid vacuum and refrigeration, right? And then we said, do not split multi-component product. Now, what are the essential first separation, essential last separation? Which split you need to do early? Making sense? Corrosive, hazardous component. Get rid of them, otherwise corrosive components stay in the process, causing corrosion in the downstream equipment, right? This makes sense? Essential first separation. What essential last separation? Perform difficult separation last. That means delta T less than 10 degrees C, relative volatility less than 1.10, difficult separation, or 1.15, 1.10, okay, 1.05. Right here. Those are difficult. You want to do it in the absence of other components. You separate them first. Okay, we have done 5 heuristics now. Let's apply to the problem. You may not be able to see this clearly, it doesn't matter. There are 2 reactions. Coming out, the 4 components, A, B, C, D. You look at HCl, benzene, kerosene, benzene. What is essential first separation? Essential first separation. Which component is corrosive and dangerous? Okay? Now, which is essential last separation? Look at the boiling point difference, okay? 214, 250, okay? Smaller delta T, relatively more difficult. That means you need more ideal stages. So, once you know this, look at next page. Essential first separation and we learn about split between C and D. delta T 36 degrees C. This essential last separation. So, you split here, get B. That's the last separation. Now, how do you compare this with the flow sheet? You want to look at the flow sheet. What is the piece of equipment you look for first? Tell me. Which piece of equipment you look for first?
The distillation columns.
I cannot hear you. Any answer? First, look at the reactor. Now, coming out, right? Coming out, you split A, then BCD. This is BCD. B from CD. B from CD. CD, C and D. Right? So, A, B, C, D. Essential first separation, essential last separation, first separation. No problem? Okay. Seventh heuristic. No, six. Seven. Removing most painful component first. This is the sixth heuristic. Most painful component first. What does that mean? Let's look at this example. A, B, C. Relative molar flow rate 70, 20, 10. Assuming equal boiling point difference, 15 degrees C. This sequence separate A first, B, C, and B and C. So, first separator, total amount of feet, 100. This separator, total amount of feet, 30. So both separated together will handle 130 units per mole per hour. How about this one? First separator 100, second separator 90. What is that? This most painful component, last separation. This is early separation. In terms of relative cost of first column, second column, and this handle less material. Better, right? Conclusion. If you have a component relative molar flow rate, largest, higher, separate them first. Making sense? All right. Last heuristics, 7 heuristics. Favor 50-50 split. £100 per hour feet. Distillate bottom. This is 50-50 split. 40-60. This is 595. Now, the split ratio, let's look at this 50-50, 40-60, 595. If this is 95, this is only 5. How do you push material 95 to the bottom, 5 to the top? You need a lot of condenser duty to condense the component to go down, right? So you look at the flow rate ratio, assuming distillate a bottom or distillate small number versus large number, you want that to be close to 1 or 50-50 split. This is called balance column. Minima, condenser, reboiler, heat duty. Amount of heat removed from condenser, amount of heat added to the reboiler. This favor 50-50 split. So now, here's the breakthrough. Next page. We call the coefficient of ease of separation. The key question is, how do you separate easy one first, or easy separation first? That means large delta T, large relative volatility. Also approach 50-50 split. How do you make both happy? Perform easy separation first with large boiling point difference or relative volatility. Approach 50-50 split, minimize the energy consumption. Now, you find out in the example I'm going to show to you, easy separation often give you highly unbalanced column. You satisfy one, you violate the other. How do you make both happy? And this is where we come up with the magic parameter we call the CES. What is that? Easy separation delta T, large, all relative volatility, -1. 1 means you cannot separate it. This is the first one, easy separation. Approach 50-50 split, we want split ratio, small number divided by large number. Okay? 30-70, 40-60, 50-50, right? You look at here, 30-70, small, 40-60, 40-60, 50-50. Now, here, you see here, I use 30 divided by 70, 20 divided by 80. Small number divided by large number, this is D over B. This is B over D. Okay? And whichever gives you less than 1, or use that split ratio. What is CES? Split ratio times delta T. Split ratio times alpha -1. Alpha, say, 1.70 minus 1 is 0.70, right? We do not like to work with decimal point. That's why I work by 100. We don't want to work with decimal point. We multiply by 100. Aha! You're now ready to solve 2 challenging problems in less than 5 minutes. Page 28. Applying the 7 heuristics. Are you ready? You can start counting. How many minutes? Okay? Okay, start counting. Example 1. A, B, C, D, E, F, G. A, B, hydrogen, methane, a single product as fuel. You can burn it. One of the heuristics said, do not split multi-component product, right? Now, let's look at relative amount. 24, 15, 46, 8. We do not have a dominating component with 50% or more flow rate, right? There's no playful component. No boiling point. All negative. So, you need low temperature, high pressure. That's why you have a compressor before the separation, increase the pressure. How about delta T? You find out split between C and D, difficult. E and F, difficult. Those allow split. Now, how do I satisfy the last 2 heuristics? Favor 50-50 split, perform easy separation first. Here is CES. Let's look at how do we get this number. Say, CES. What is the CES? Split between AB, CD, F, G. AB, CD, F, G. Flow rate ratio, 18 plus 5. 24 plus 15 plus 14 plus 6 plus 8. Right? Boiling point difference, 57 degrees C. The answer is 19.6. What if we make a split here? What do we consider here? Let's think about it. This is no. You do not want to split multi-component product, right? And CD is last split. EF is last split. Why? 16.6. How about the remaining option? Remaining option here and here. No. ABC, yeah, here. There's also one here, right? Remaining options. So, question here, question here, question here. You look at the split. AB, between AB, no. BC, we do not know yet. CD, last. No, CD is last. You don't want it. You don't want it. DE, question mark. EF, last. Between F and G. So, okay. We need to investigate between B and C, between D and E, between F and G. Right? AB is no. Right? B and C, we do not know. CD last. D and E, we do not know. EF last. E, F, and G, we do not know. So, I got the second one, A, B, C, D from E, F, G. Okay, A, B, C, D from E, F, G. 18.00. No. 14 plus 6 plus 8. 18 plus 5 plus 24 plus 15 is this number divided by that number. This sum divided by that sum, small number divided by large number. And between D and E, 40 degrees. Now let's try one more. A, B, C, D, E, F from G. That's the last one we want to investigate. A. Then this one, 18 plus 5 plus 24 plus 15 plus 14 plus 8 times 41. Answer is 4.0 right here. Do you know how to calculate it? CS value of potential split. Once you know this, which one is the first split? The larger one. Okay, go to page 29. So, a split here. Now, we know C and D is last. And E and F last, right? So, this last, that's last. What are the remaining options? Question mark, question mark. Question? So, let's go to the next page. How do you determine this? Split between C, D, E, F, G, or C, D, E, F from G. Here, C, D from E, F, G, C, D, E, F from G. Two question marks. Right? So, flow rate ratio, 28 to 39, 8 to 59, delta T, CS, multiply the 2. Now, here's a crucial thing you need to understand. Perform easy separation first. That is slightly larger than that. Suggest you do this. That is bad. Why is that? This easy separation give you a flow rate ratio of 8 to 59, highly unbalanced column, high energy consumption. If you choose perform easy separation first, that one. But just end up with a highly imbalanced column, the magic parameter CSS. Never listen to that guy. You see this CES is much better. This is easy separation plus 50-50 split. Much better. Right? So, with this, the answer CD for EFG, CD, last separation, EF, last separation. You got this? This is our answer. In the beginning, this is our answer. How about the other answer? In the beginning, let me find it. What do I get it? Let me find it. Ooh. All right, I found it. This is our answer. Right? How about this one? Remember, we found the CES from last page. 18.6, 18.1, right? This is the second best initial split in terms of easy separation for 50-50 split. If we decide to do this, the rest is history. Fine? A, B, C, D, right? AB is single product. CD is last separation. The only split you have is right here. That's what happened, right? Here, EF is last separation, right? So the only split is right here, right here. Just take that like 1 minute, right? So I got both solutions. Tell me how many minutes we did? Did you count it? Is this easy? 10 minutes or longer? I was explaining slowly. You like it? Okay. Give me a 10 minutes break, 4:15, before I explain this one. Relative, 36, small, relative, 135, that's
I bet there's, like last year they had like food trucks.
AP. Yeah, zero.
We went grassroots market, go around, we went to table. Yeah, I usually just not too fan of the yelling, but I think it's actually. Yeah, I can. I think the yelling's kind of cute.
I just know. These typed up notes are not going to be it.
Yeah, my handwriting isn't the most illegible, I don't think, but.
I mean, I think I've got plenty of practice decoding Dr. Blue earlier this
Okay.
week, so I'm sure you'll be fine.
Really? All right, let me see. That was the bad, like, distracted.
It might take a while. I also. It does keep. I see a lot of
They've got Ferris wheel, the performance zone. I guess it's like a stage. Sponsors. Cycling. Well, yeah, they say no title. It's like it's like brand new Atari. F-19 fighter jet.
And then like, what do you mean? I'm getting my ruler out and then I'm drawing.
Unstoppable force.
Okay. Let's get started. We want to finish in less than 40 minutes, okay? Example 2, page 31. Oh, ow. This problem using two methods, attractive distillation, ordinary distillation, solvent, furfural. You look at this problem, desired product, DE, single product. No split between them. And most playful component is C. Most difficult separation between C and D. So there should be the last split. You add the solvent, relative volatility improved to 1.70. How do you decide the possibility A, B, F? You do not want to split CD yet. That's a challenging one. You do not split between D and E, single product. So, three possibility. How do you decide which one to do? This where we use CES. Let's take a look. A, B, C, D, E, F. Split ratio times relative volatility minus 1 times 100. Just add to 100. That's good. 1.47 A. B, C, D, E, F. 98.53. Relative volatility, 2.45 minus 1 times 100. That's what this 2.163 come from. Split between B and C is not written here. So, A, B, C, D, E, F. Method 1 equal okay, AB, that is 1.47 plus 14.75. 100 minus 1.47 plus 14.75. Relative volatility minus 1. 1.18 minus 1 times 100. That is 2.485. That is this one. And A, B, C, D, E from F. That is this. F, 5.90. 100 minus 5.90. 2.5 minus 1, 9.404. So, let's go to page 33. D single product, CD is last. What do we split? Here, here, here. This is the largest. Right? So, this is the last. F from A, B, C, D, E, right? Now, A, B, C, D, E. D, E, single product. C, D, last. So, the option remaining, we need to investigate A from B or B from C, right? A from B or B from C. Look at the top. A, B, C, D, E. A from B. A, B, B from C. You want to investigate where to split this A, B, C, D, E. D is the last. C, D is the difficult last. So we have an option A from B, C or B from C. Here's one question mark. Here's a one question mark, right? Flow rate ratio alpha minus 1 times 100 CS. That's larger. Now, here's another trouble. If you follow the heuristic, perform easy separation first, relative volatility 2.45, and this relative volatility is 1.18. You would do this. Now, this end up with, I don't want to use highly, I want to use extremely unbalanced column. 1.47 versus 92.63. That's no good, right? But that's exactly previous method advising you to perform easy separation first to go with this. It's no good. This one is better. Larger CES, even though it's not easiest, but flow rate ratio is more reasonable compared to that. So, AB from CDE, right? So, AB from CDE. CD, last. DE, single product. That's easy. Just add the solvent. Add the solvent. Split C from D. Okay, D is single product, split from the solvent. This is our solution. Does that make sense? Okay, let me emphasize to you a very important point, page 34. Example 1, example 2. Perform easy separation first. I'll tell you this, easy split first. Favor 50 split. And this larger CES favor 50-50 split. This larger CES favor 50 split. Word of wisdom. Whoever telling you to perform easy separation first, wrong. Understand? Favor 50-50 split first. That's a wise man. Now, give you, that's your separation process textbook, right? Philip Venkat. Page 263. Do the easy separation first? No way. No way. Now, here's my friend. We all went to Princeton, so I wrote him a letter. He replied to me. I'm not an expert in heuristic. I missed your wonderful article. That's why he did not revise his textbook. Understand this? Wise man is hokey. All right. What's your impression about heuristic senior design? All common sense. Heuristic. Okay? You need to think common sense. We got a homework problem, let me explain to you. Okay, let me see how much time. Oh, 15 minutes or less. That's good. Page 37. You may not see this clearly, that's okay. Now, some students said, can you type out this class notes? I don't have time. I live from one deadline to the next. Right now, all my time is to help you go to the expo. So I have to finish your resume, okay? After September 10th, and some people say, I cannot come to the assigned section for aspirin training and so on. I said, wait until middle of September. We deal with that later. Easy. I give you a list of student name, email. You find a friend in the other section, switch with you. That's all. Right? But those things can wait until middle of September, right? And I don't have time to type this thing, okay? Every week I have different deadline, okay? So do things one thing at a time. Okay, let's look at this. You want to type it up for me, give to me, or future class for benefit. Okay, I don't have time to do it. All department secretary, 20 years ago, I have a personal assigned person secretary. Type everything. Right now, they don't do anything. Okay? That's the trouble. All right, don't complain. Let's look at this problem. You have A, B, C, D, E. Carbon 3, IC4, NC4, IC5, NC5. You see here, propane, isobutane, N-butane, isopentane, N-pentane. 5 component, right? Given relative volatility relative to the highest boiling component. So, alpha ij. You look at here, alpha carbon 3 of K carbon 3, K IC4, K NC4, K IC5, K NC5. Okay? So relative volatility with reference to the highest boiling component, 8.1. What is 8.1? 8.1 is KC3 divided by KNC5. What is 4.3? KIC4 divided by KNC5. All is a reference component NC5. But when you apply heuristic, you need relative volatility, carbon 3 to IC4, right? That is KC3, KIC4, right? That is KC3, KNC5, KIC4, KNC5. That is 8.1 divided by 4.3. Do you get it? So, first you need to convert this to a table using alpha ij. Okay? So, you will have alpha C3 IC4, alpha IC4, NC4, alpha NC4, IC5, alpha IC5, NC5, right? That's what you use in applying heuristic, to split between the two. That's the first thing. Now, the problem is that we have this actually is the PhD dissertation from California, Berkeley. A PhD student spending 3 to 4 years solving this problem. It said, best sequence, second best, third best. Explain to you why this is best, why this second best, why is third best. You are assembling heuristic, right? So, heuristic, number 1, number 2, number 3, number 4, number 5, number 6, number 7. Do you remember what they are? Favor ordinary distillation, right? Avoid vacuum and refrigeration, right? Do not spend more than component product. Remove corrosive species first. Perform difficult separation last. Remove most playful component first. Favor 50-50 split. I hope you do not memorize it now, but after you have done homework assignments over time, you know what they are. I know because I wrote a paper, right? So now, sequence 1, 2, 3. 1, 2, 3. You can apply it. Find out this one. Yes, 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 yes. And you can also quantify them by finding CES value of relevant split, as I did in the example. Okay? You want to decide, for example, why do you split ABC from DE? Favor. Why not A from BCDE? This better. You just go to check the CES value. And this is second best because this both apply a high CES value. And this A from BCDE, poor CES value. Now, what's the difference between the two? B from C, A from B. How do you compare the two? CES, A from BC, CES, AB from C. Set up a table, right? You have the split ratio, D over B, alpha minus 1 times 100, and this is CES, right? And obviously this has higher CES value. Okay? And the same thing happened. And tell me, based on satisfying heuristic guidance, relative value or CES, such as this example here, you tell me why is best, second best, third best. You did that, you earned your PhD degree. Okay? Simple heuristic. You get a PhD thesis. Done. Okay? Any question? Okay. Page 38. Now, you look at this. Don't split. Multi-component product, right? So, now it's a single product, right? You have the potential split right here, right here, and right here. Three options. You have flow rate, look for boiling point, Google it. So, CES equal, right? You can find out, develop the sequence. Product 1, benzene the product, toluene product, okay, fourth product. This one is easy. Any question? Now, you got question, you can email me, and as long as I'm awake, when I sleep, I have my iPad next to me. When I wake up, I check it, 3 o'clock, 3:90. The student was submitting a memo. She would be surprised and respond in 10 minutes. What? I just happened to wake up. I look at the iPad, I know what went wrong. Okay? As long as I'm awake, you can respond. If not, you know I'm sleeping. Okay, have a safe weekend.